All right, in this lesson, we're going to take a quick look at direct versus inverse variation, or proportions. This is helpful when beginning a look at gas laws in grade 11 or grade 11 advanced chemistry. So suppose you have two variables, A and B. Okay, we'll just speak generically right now. You have two variables, A and B. And we're going, now in chemistry, those would be pressure, temperature, volume, moles of gas, things like that. But we're going to speak generically. So let's suppose we have a direct variation or a direct relationship between them. Okay, so we're supposing a direct relationship. What does that mean to say that they're directly related? That means that if A, the first variable, increases by some factor. So suppose it were to double. Then B, the other variable, would increase by the same factor. Now I chose increase arbitrarily. That could also be decreasing. If A were to decrease by some factor, so maybe A is decreased to be 1/3 of its original value, then B would also decrease by that same factor. Now what does that look like graphically? Okay, so suppose you collected some data and you had a table of A and B values, and you went and made a graph of A versus B. What you'd find in a direct proportion is a straight line relationship like that. Now we all know the equation of a straight line that passes through the origin like this would be y equals mx, right? The y-intercept here is 0. Well, on this graph, we have, instead of a y, we have an a. So let's say a equals, and instead of an x, we have a b. So let's replace the x with a b. And now in the letter M stands for slope in math, and let's leave it as M for slope and just put a different letter in here. We'll use the letter K just for a constant, a proportionality constant. So this, A equals KB, is the algebraic form of a direct proportion. Okay? Now on this line, the slope of the line would equal the constant K in my formula, right? The M is equal to K. So A equals KB gives you a direct proportion. Now, if you rearrange that equation and you solve it for the constant, you'll find that K is equal to A divided by B, which means whenever you have an A and a B value together, if you divide them like this, you'll get the same value. You get K as a constant. So if you had a data table with 5 values of A and 5 values of B, every time you took an A and divided by a B in your data table, you'd get the same result. You'd get this constant. But that means if you had an A1 and a B1, so one pair of values from your data table, and divide them, that would equal K. But also if you took another pair, A2 divided by B2, that would also give you K. So logically, if they both give you K, then we can conclude that an A1 divided by a B1 must equal an A2 divided by a B2. And that would be another way of thinking of a direct proportion. So you want to think about 3 things here with direct proportions. Number 1, a graph of A versus B. This graph here, A versus B, will always be a linear graph going through the origin like this if you have a direct proportion. Secondly, because that graph is linear, you get an equation that A is equal to KB. And finally, you can rearrange that equation and use logic and derive the idea that A1 divided by B1 equals A2 divided by B2 in a direct proportion. Now, the other major type of relationship is an inverse or indirect proportion. So an inverse relationship. Sometimes this is called an indirect relationship. So what happens in an inverse relationship? Well, when one variable increases by some factor, so suppose your A value were to double, then the other variable decreases now by the same factor. So in other words, if you were to make the A values 3 times bigger, then you'd find that the B value is 1/3 of its original value. So one variable increases while the other one decreases proportionately in an inverse relationship. So what kind of graph would you see if you graphed A versus B in an inverse proportion? Well, we know that when A's get bigger, the B's get smaller. We know that when the B's get bigger, the A's get smaller proportionately. Well, in a pre-calculus math class, you would realize that that relationship produces a curved graph like this, and that is actually 1/2 of what's called a hyperbola. A hyperbola. I say it's 1/2 because in chemistry, we're only dealing with positive values for A and B. In a math class, you'd extend your graph and have negative values for A and B, and there'd be another piece of the hyperbola down in this third quadrant, just mirroring the one in the first quadrant. But in chemistry, we're not going to see any negative pressures and negative volumes, etc. So for us, we'll only see this first quadrant graph if we have a hyperbola. All right, now the equation of a hyperbola, you're probably not as familiar with like you would have been for the equation of a straight line. The equation of a hyperbola looks like this: y equals k divided by x. Okay, so in our graph, we don't have x and y, we have a's and b's. So for us, we can say a is equal to k divided by b. That would be the one version of the algebraic equation that describes an inverse relationship. If you compare that back to the direct relationship, there we had a equals k times b, but now that we have an inverse relationship, a is equal to k divided by b. So notice in an inverse relationship, the a is in the numerator on one side, the b is in the denominator on the opposite side. So when one gets bigger, the other will get smaller. So that's an inverse relationship. Now, if you were to play that same game of rearranging that, we could say k, the constant, is equal to a times b, which means whenever you take a pair of values from your data table, if it's an inverse relationship, then the product, a times b, will always give you the same answer, this constant k. So if you had an a1 times a b1, to a 1 point from your data table, and you multiplied them like that, you'd get k. If you had another pair of values, another data point, rather, a2 and b2, multiply them, you also get k. But therefore, logically, an a1 times a b1 would have to always give you a2 times a b2, since they're both equal to k. So there is another algebraic version of the inverse relationship. Now, one more thing. If you look at the version that we already wrote up here, a equals k divided by b, you could take that equation and you could just rewrite it slightly. Instead of a equals k over b, you could write it as a equals k times 1 over b. Okay, compare those and you'll see they're the same things. And why would you write like that? Well, if you think of it like that, you can now look at that equation as y equals mx, which we reminded ourselves a minute ago is the equation of a straight line. So therefore, where the graph A versus B gave me a hyperbola, so this graph is one version of the inverse relationship that you want to remember. A graph of A versus B would be hyperbolic if it's an inverse relationship. If we made a new graph, this time instead of A versus B, we keep the A as the y values, but now on the x-axis, we're going to graph 1 over b, right? The a's are our y values, and 1 over b, the reciprocal of B is the x value. In this graph, we should see a straight line relationship. So in this graph, we get a linear relationship if it were an inverse proportion between the variables. And just like before, the slope of this line would give me the constant k. So we see here 4 different things to remember about inverse relationships. The graph A versus B is a hyperbola. That equation is A equals K divided by B when written algebraically. When that's rearranged, you get K is equal to AB, which led to this logical conclusion that an A1B1 has to equal an A2B2 in an inverse relationship. And finally, while the graph A versus B was hyperbolic, the graph of A versus the reciprocal of B would be a straight line graph. And the slope of that graph would be the constant K. So those are the things you want to remember about inverse and direct relationships between variables. When we study gas laws between pressures, volumes, temperatures, and moles for gases, when we pick any pair of variables from those 4 variables, we find that the relationship is either direct or inverse. So when you know these 2 relationships, you can apply it and create the gas laws yourselves. So that is an introduction to direct and inverse proportions for gas laws in chemistry.